Well, good afternoon and welcome back to the final webinar in the series this year. We thank you for attending. If this is your first one, thanks for joining us. If you've been attending throughout the series, thanks for supporting us in this, and we hope that you found these webinars valuable. We are recording these. These will be available to you at if you visit aiec.coop/webinar weeks. There's an archive link on there that you'll be able to access all of our webinars that we've provided this year. Again, if you have any comments, please drop us a line. Let us know what you think. Also, suggestions for next year's content as we're looking forward to potentially running these again in the future. Hopefully, within the next week or so, you should be expecting a survey from Miss Ashley Graham. She'll provide those to you if you have a couple minutes. Fill those out, and that will enter you in a drawing for a prize. So look forward to that. Finally, for our last today, we have Premier Power Maintenance presenting on maintenance of your electrical system for maximum reliability. This presentation will last roughly 45 minutes. And we'll leave some time for questions at the end. However, during this presentation, if you have any questions, please submit those to the chat function. You may send those directly to AIEC, and we'll present those and moderate those to our presenter. If you, please keep your microphone muted. I'm sorry, please keep your microphone muted unless our presenter asks. If he opens up the floor, it's perfectly fine. Go ahead and unmute yourself, and we're okay with some open dialogue in that case. Otherwise, if someone has some questions on PE credits, Brian?
Yeah, if you've not already done so, just shoot me an email at badams@aiec.coop. I think I have most of you, but if you haven't, just shoot me an email so I can make sure to get you your PDHs. Hopefully later this week, if not next week, I'll be sending those certificates out. So it'll have your PDHs for all the webinars that you attended. So shoot me an email, let me know. Our presenter today is Alan Holt. Alan is a licensed professional engineer in the states of Indiana, Kentucky, Ohio, and South Dakota. He has a BS in electrical engineering technology and an MS in interdisciplinary engineering from Purdue University. Alan's working career includes 29 years at Indianapolis Power and Light Company in various engineering, operations, and supervisory functions. Since his retirement from IPL, he has worked for various electrical contractors and is currently employed as a director of training at Premier Power Maintenance Company at the corporate office in Indianapolis. So with that, I'll hand it over to Alan.
Good afternoon, folks. So thank you for joining. So today we are going to talk about the maintenance of your electrical system for maximum reliability. Now, when we talk about maximum reliability, industry is really faced with a challenge of improving or at least maintaining their reliability, oftentimes within the aging infrastructure. Even this challenge, it comes oftentimes with constraints, workforce constraints. You have the facility manager, then you have the operations manager, and they don't see eye to eye, and the operations manager really doesn't understand why you'd want to take down a system that's functioning properly now just for the idea of maintenance. And so that conflict goes on, and it has been around here for a while. So this paper, this presentation is a multi-faceted approach to system reliability, how we should actually be looking at it and what we have to do to maintain system reliability. And we'll talk about principles and processes for doing that. So the first thing we want to talk about is reliability principles. We have simple series and parallel system reliabilities. We have the series system here on the top where we have three components, electrical components in series, and then we have the parallel system down here on the bottom of the slide, which we would have parallel paths in order to get to the end result. So when we talk about these principles, in that series system, if you look at the overall system reliability, it's simply a multiplication function of the reliability of each individual component. So for instance, the slide that I have on the screen now shows that each individual component has a reliability of 99%. So if I look at that and do through the math, then the overall reliability of this system is 97%, which is pretty good reliability. But if we look at that and we reduce it just a little bit, if each system component had a reliability of only 97%, then the overall system reliability at that point in time would only be 91%. So there'd be a great reduction, even if one of the series items had a lower percentage of reliability. Now, when we look at the reliability with regards to parallel systems, we have a totally different equation here. And I'm not going to spend a lot of time on equations because that can just eat up time and it's boring. But in this situation, we start out with each individual component having a reliability of 99%. And we look at the overall system reliability, it's almost 100%. And even to the point, if we took each individual component of this system and the individual components were reduced all the way down to 75%, the overall system would still be 98.5% reliable. So we can understand the concepts here, and we glean from that. The summary is that in a series system, the reliability is always going to be worse than your most unreliable component. In that parallel system, the reliability is going to be better than your most unreliable component. So we bring that up just so we can comprehend what we're actually looking at when we look at our own systems. Each of us have series components in our systems where we would have a single point of failure. And that's where we're going to focus a lot of our time today, is talking about those situations where we would have a single point of failure that could cause us a real problem. Now, reliability principles. Reliability comes at a cost, okay? And it's obtained by several different components. It's obtained by the design of the system. Hopefully we do a good job of designing that. It's obtained by how we operate our existing systems, and hopefully we do a good job of that. It is maintained and obtained by how we maintain our systems, and certainly it's obtained by the equipment that we actually purchase, the equipment that we actually install in our system. So let's look at the design. If you have the opportunity to be part of that design, then we need to actually be able to design a system where we have multiple components that are parallel in nature. We need to operate our system so that every single component is operating within its standard design limits. We need to maintain that equipment to the point where we can understand that we can expect several more years out of it. And we need to do a really good job of what we are actually purchasing when we purchase that equipment. Low cost, low bid is not necessarily the most appropriate thing to do when we're talking about trying to develop a reliable electric system. So we've spent a little bit of time on that, but I want to talk a little bit more about the reliability principles. And when I talk about reliability principles, I want to talk about reliability versus complexity. You know, my mom and dad had one of these phones, and they used that phone for a long time. And even up to like 12 years ago, they still had a phone like that similar in their house that still functioned right. This is our phone today. I think my phone's pretty reliable, but I don't think it's going to last the same length of time that my mom and dad's phone did in their house back in the day. I bring that point up because there's many things that happen in our industry today that we have very complex systems. For instance, one thing I want to mention is protective relays. You know, if you look at today and you go out in the market and look at protective relays, everybody wants to jump on board on the newer electronic relays, the microprocessor-based relays. It's like they do some great things. You want to talk about complex. It's like I can remember back in the 70s when I was a relay engineer at Indianapolis Power and Light Company, when we were working with the electromechanical relays, and I could take that relay manual back to the motel room at night and read that manual, and it was 15 or 20 pages long. When you look at a relay manual today on one of those microprocessor-based relays, it's 300 pages long. It is complex. That relay can do pretty much anything that you could possibly want to do. Sounds great. But here's what I want to say. If you take that old electromechanical relay, we're still testing those things that are, some of them are approaching 70 years old right now. I am absolutely for sure, without any doubt, there's not a microprocessor-based relay that you're going to install today that's still going to be in service 70 years from now. So when you want to talk about reliability, I can't beat that old relay. Now, if you have functions that you need the brain work of that microprocessor-based relay, if you have the need for that information, if you have the need for that complexity, then go ahead and do that. That's great. That's a need that's been met. But if you're looking simply at reliability, understand that complex is not necessarily reliable. Just a point on my soapbox. So let's look at needs and need assessments. So when we look at what we desire and what we need, those are two totally separate things. So we can have cost justifications for all those things that we need. What truly is acceptable for us in the operation of our electrical system? Is there truly a need for the entire system to be a certain reliability, or can we have different sections, different requirements for different sections? Are we looking at the situation where no downtime is acceptable versus quick restoration? Now, I go back to my old utility days. It's like we wanted a reliable, robust transmission and sub-transmission system, but when it got down to the distribution, we were in the mode for quick restoration because we didn't want to spend all the time for maintaining all the part of the distribution system. And then we look at protecting the equipment versus downtime. Now, I know of people, and I know of companies that do everything possible to make sure that their equipment fully operates at all times within its nameplate criteria. And I do work at a facility right now where the main incoming infrastructure to that facility, the facility was built in 1941, and it's still being fed today by two Allis-Chalmers 1941 transformers. That's the main feed for this facility, and they still test good. They're still there because the customer has always operated those transformers within their nameplate operating constraints. That's not always the case. Sometimes we as customers need to understand that we can exceed those from time to time, and the exceeding will take away life. So we need to take that into account. So need versus desire. And again, that often goes by which hat you're wearing. Are you an operations person, or are you one of the maintenance facility people? So those characteristics, those criteria, those questions need to be addressed. So here's one of my soapboxes. Reliability is an asset. Oftentimes in hard economic times or even robust market times, we choose to not maintain our equipment. We choose to take part of the asset out of our electrical system in order for saving money or to meet production criteria. That's a decision that can be made. Just we always need to understand that it is extremely, extremely difficult to get that value back in that system. So it's hard to put that asset back together after you've taken part of it out of it. So we've talked about a couple of very simple reliability principles. We've talked about going through and truly understanding what our needs are for the system. And so now I'd like to talk a little bit about system assessment. So when we talk about assessing our system, we need to be able to identify the weak links that we have in our system. What are those weak links? Single points of failure. Anytime that I have a place where one component can cause me harm, that is a weak link. So we need to understand what those are and take appropriate measures to reduce that risk. We need to know our equipment. Generally, what we've got, we pretty much always know generally what we have as a system, but specific pieces of equipment. We need to understand the history with the types of equipment we've got. Most of us get in the mode where if we buy one transformer and we have good luck with it, we stay with that manufacturer and we try to stay with that, so we limit the number, and that's great, and that works very well. But we need to understand our equipment and understand what the specific natures of those are and what kind of history do we have with that particular piece of equipment, and keep that maintenance record on hand. What equipment do we have that we are really abusing at this point in time? And we all have systems where we do abuse part of our system, so we need to take care of that. We need to review ourselves with past test reports. Now, this is something that my company reviews quite closely. It's okay to do a test on a transformer, or okay to do a test on a battery, or okay to do a test on a cable or a circuit breaker. It's okay to come back for that test and say, you know what, this tests, all the tests we've done have met the criteria for all the standards that we deal with. That's great. But we need to also always look back at the past test reports. It may meet the existing standard, but if the past test report looked a lot better than what we've got right now, we need to notice that the equipment is deteriorating, even though it's still acceptable for service. So that's something that a lot of people overlook. We just got a good test, it looks good, that's okay, but how is it now compared to what it was? I can relate to that as being a 68-year-old going to the doctor. It's like the doctor says everything's good. It's like, well, it may be good, but it's not what it was 40 years ago. So there's a deteriorating process there. We need to go to outside resources. For instance, certain bushing types, there were years ago, it's like the GE type U bushing, everyone in the industry knew that there was a problem with those bushings, and most utilities went through the process of replacing those bushings before they had a failure. My company was doing that as well, and unfortunately there was one transformer we were about 2 weeks short on getting it replaced before it failed, and we lost the transformer for that. So staying in touch with the outside resources, the community that we have, to understand what downfalls certain pieces of equipment. And we always need to understand that even if we have a great design, it can still leave room for improvement. So I've got some examples of oops. There's a hospital that I do some work with, and reliability is of utmost importance. And so here is a simple one line of a main distribution system inside the hospital. They have two sources, source A and source B. They even went to the point where they worked with the utility, my old utility, Indianapolis Power and Light Company, to make sure that these two sources were fed from different substations, okay? So one substation wouldn't hurt it. Everything was PLC controlled inside this system, okay? PLC, so it would notice that if we lost source A, it would open up circuit breaker A and close the tie so that there would only be a momentary outage. It would recognize when it came back and go that way. All PLC controlled, very good. And it was so secure that the manufacturer had the foresight to put a UPS system there, so that even if the source died, that UPS would be providing power for that PLC controller. And also that UPS would provide control power for the breakers. It looks like it's, the most secure system in the world. But guess what? When we talk about that single point of failure, the UPS they installed in that system was one very similar that you could buy at one of the big box retail centers for about $99. Well, it wasn't made to last forever. Well, the PLC, they did some special programming in that. So one of the programs in the PLC says, you know what? If we start losing voltage on this UPS, if it starts declining, we want to make sure that we trip all these breakers before they can't trip anymore. So sure enough, about 5 years after it was placed into service, the UPS started dying, voltage started declining. PLC noticed the voltage drop and decided to trip all the breakers so that it would make sure that they could operate before the voltage was gone. That certainly wasn't what the hospital desired. So looked like, it looked like a steel project that nothing could go wrong on, but that single point of failure, that was there. There's another system I went and looked at and was called out on in the middle of the night. It was a data center. It was a large data center, okay? In this data center, they had a utility feed over here. They only had a one utility feed because it was located in a little isolated area, but they had an enormous UPS system to feed their facility. And that UPS system was built to withstand a 40-minute outage. And they had an emergency generator here that could carry the full load of the system. Wow, looks rock solid again. Main breaker for the UPS, main breaker for the generator, automatic transfer switch that they maintained and tested on a quarterly basis. Here, what happened? They built the system and all of a sudden they kept adding load. Adding load. So the load kept adding here for the data center, but they never reviewed anything like that. And eventually the load got so large that this breaker feeding the data center tripped. They did not lose utility power. They did not use the UPS. The emergency generator was still there, but they lost their system, and it was a long outage before we could get it back up. Again, a single point of failure. It's one of the situations where this breaker should have been designed to trip after these two breakers tripped. This is the last thing in the world you want to trip. You only want it to trip before you damage the switchgear itself. To my way of thinking, if I'd have been designing that, I'd have put a piece of copper bus in there and let the other two breakers go. But it's just another example of, you know what, we think that we have a solid system here that nothing could possibly go wrong with, and yet it can. It can. So let's talk about some specific components of electrical systems. The first one I want to talk about, checking my time here, the first one I want to talk about is the battery system. It is the heart and soul of your protection scheme. That battery is the most important thing that you have in your substation system. And we have industrial customers that just truly don't understand that. I actually got called out one night to a large industrial facility where they had a battery that hadn't been maintained so long that actually one of the leads corroded off, and for an interim they just came in and they plugged in a battery charger and put the battery charger in the place of where that battery had been. It didn't last the entire night, and that was a real problem for them. So when we talk about design of the battery system, that has changed so much. What are our critical loads now? What critical loads do we have to have? What do we have to carry on? Again, with the new microprocessor-based relays, they're energy efficient, but that's a load that we never had on before. We just had light bulbs when I was a relay engineer years ago. How long is that battery to last? Okay, so how long of an outage do you stand, and when do you want it to be able to perform? Back in my old utility days, our batteries were designed to last for a 12-hour period. No power, 12-hour, carry all the load, and after 12 hours still be able to operate anything. What kind of charger do you have? What kind of monitoring on that charger do you have? Is it a battery eliminator so you can actually do some battery maintenance in good weather? And what kind of environment do you have that battery in? Those are all questions that need to be looked at during the design of the battery system. Even after the design and the install, again, it's the most important piece of equipment that you have in your electrical system. There are monthly checks that need to be done. And that's one of the first things that companies tend to knock out of their budget are these monthly checks. Float voltage, measure the battery terminals, pretty simple, doesn't take a lot of time. A good visual general inspection of the battery and the charger, make sure everything's working there, make sure that there's no lights on the ground, Make sure there's no ground on that battery system. Check the charger output voltage and current. Monitor the electrolyte levels, and do a pilot cell. Take voltage, temperature, and specific gravity of that pilot cell, and make sure all your battery monitoring systems are operating correctly. Doesn't take much time, but you have to get to your various sites to do that. Then on a quarterly basis, do all those monthly checks, and then do voltages of the cells, and 10% specific gravity. Do the specific gravity of at least 10% of the cells, and the temperature along with those. Again, it's still the most important part of your system. And on annual tests, do all of those monthly and quarterly checks, and do the specific gravity of each specific cell, the voltage on each cell. Check the terminal connection resistance. They can still look good, but we can have some resistance increases there that are really a problem. And one of the easiest things for us to do is to have a device that will check the impedance of each cell. That's a true indicator of how the system is going. True indicator of how the system is going. I hit the wrong button here. When are corrective actions required on this battery system? Well, anytime the visual inspection doesn't look good, that's an indication that we need to do some corrective action. If the terminal resistance of any one of those terminals, if it's 20% above the installation value, or if it varies by 20% over sister cells in that same unit, then that's a problem. Individual cell readings, and people just truly don't understand this sometimes. If you look at the overall string voltage and divide that by the number of cells, you will get a voltage for the cells. Say, for instance, each cell is about 2.24 volts per cell. And that's a typical float voltage for a lead acid battery. If the voltage of any one of these cells varies by more than 0.05 volts, and that's a pretty minute variance. If there's a variance of 0.5 of a volt on one of those cells from the string average, then that's reason to take corrective action. That's an indication that we've got a battery that's that's very sick, that we need to correct before we make sure, before that that section of the battery system actually fails. So even individual cell voltages are important. Specific gravity. If the specific gravity after correction, this temperature corrected, if it drops before below the manufacturer's minimum requirements, that's the need for corrective action. So the second topic I want to talk about with regard to specific sections of reliability is the transformer. Let's talk about reliability and obtaining expected life out of a transformer. We get hired oftentimes to come out and the customer wants us to do preventive maintenance. Well, we need to discuss what the difference is between preventive maintenance and predictive maintenance. Almost all the tests that we do are predictive in nature. We're not preventing anything. We're just telling you the current status of this piece of equipment, okay? So most tests are predictive in nature, and they give you an indication of the anticipated condition. There's nothing preventive about that unless you take corrective actions after the testing is done. The testing itself is not preventive in nature. So if I look at a transformer, we can talk about really in-depth maintenance programs, but if I want to talk about a preventive program, here is the preventive program. Operate that unit within the proper load limits. I can very well remember summertime. This would have been 40 years ago in my career. It was a really hot summer. We lost a transformer in one of our substations. We had another transformer in that substation, and we picked up the load on another transformer, but it was extremely overloaded. And we're actually out in the sub yard with a hose spraying water on the radiator fins of that transformer to try to keep the temperature down. I know, I understand that sometimes we have to exceed load limits, but if you want to keep the life of that transformer approaching that 50-year life that we'd really, really like to have, it needs to be operated within the load limits. Maintaining the temperature at or below 65 degrees, 65-degree rise. That's important in the operation of that transformer for extending its life. If you start going above that, it's not a linear relationship, it's an exponential relationship that you're taking the life out of that transformer. And the biggest thing that you can do is eliminate through faults on that transformer. Through faults are the #1 cause of immediate death. Make sure you have appropriate lightning protection on the transformer. Make sure that your relaying system acts correctly and functions correctly, and make sure that you properly maintain the internal atmosphere. So if I look at this, the three that I want to look at is like, I want to make sure that I operate it within the load limits. I want to make sure that I do my best to eliminate any fault possibilities. I want to make sure that my relay system works, and I certainly want to make sure the internal atmosphere of that transformer is always carefully maintained. So if we can follow this simple plan, we will eliminate up to 85% of the transformer failures that we typically have. If you get rid of that fault possibility or reduce that, that would have the greatest impact that you could possibly have. Operating that system as we've indicated, the preventive maintenance system, the life expectancy of that transformer should be at least 50 years. Now, if you're working with customers that have furnace transformers and rectifier transformers, they have 6 times the failure rate. They're not operated on an ideal basis. So, side note, another soapbox from Alan. I have quite a few of these. Even though that your transformer may not be operated in an ideal environment, attention to the simple plan will pay you huge, huge dividends going forward. One of the easiest and simplest things that we can possibly do for a transformer is to test the oil. You know, there are 2 different types of oil tests that we perform. One oil test is called an oil quality screen. And we can do that oil quality screen. That oil quality screen is actually for testing how well the oil is. And we can do dissolved gas analysis, and then we can also do electrical tests as well. We're going to spend a little bit of time talking about the oil test that we want to do on this transformer. First of all, we need to know the enemy and meet the enemy face to face. Okay, the enemy of this transformer, 3 main things: moisture, oxygen, and heat. If we can eliminate moisture in that transformer, if we can make sure that we don't have oxygen in that transformer, and we can maintain the heat level in that transformer, we've done a lot to save and prolong the life of that transformer. Moisture is the most common cause of deterioration that we have. It decreases the dielectric strength of the oil, obviously, but that's not the whole problem. The fact that moisture is in there in the first place, if it meets with oxygen, so now we have oxygen and moisture, that's going to cause a situation where that we call oxidation. And when oxidation begins, if it's not corrected quickly, long term, it will build into sludge. And that sludge forms on the paper that's around our coil assembly inside the transformer. And when that sludge is there, then part of the purpose of the transformer oil in the first place is to keep the temperature down. So now I've got sludge there, and I can't get rid of all the heat on that paper and coil assembly. And when the heat increases, the rate of oxidation increases. So every 10 degrees C doubles the oxidation rate. So basically, if I have moisture and oxygen and I add heat to that, I'm on a death spiral, because now I'm just creating more sludge, which increases the heat, which is causing oxidation to increase rapidly. Sludge sticks to the surfaces where the heat normally is, where the heat's normally dissipated. It creates more heat, accelerates that process of oxidation, continues to build up more sludge, will actually end up with insulation failure. And acids in the oil, one of the simple things we can do on an oil quality screen is look for the acids. That's one of the first indications of sludge buildup. Good news, if you do testing, at least annually on your transformers, if you catch the moisture early, it can be remedied by filtration. Second bit of good news, in the absence of oxygen, in other words, if you've got a good nitrogen blanket on top of that transformer and that transformer is tightly sealed, without oxygen, you can't have oxidation. Therefore, make sure your transformer is tightly sealed and has that good nitrogen blanket. The oil quality screen, the whole purpose is to test the oil, make sure the oil is satisfactory for this intended purpose. And so this intended purpose is to insulate and keep cool. So here are the tests we're going to do. We're going to do a dielectric strength, which is a KV test. We're going to do a water content. We're going to look at acid. We're going to look at interfacial tension. We're going to look at visual and specific gravity. All those tests. And again, all we're doing is looking at the quality of the oil in that transformer. Now, I have some analysis tools that I've taken from various groups, the IEEE and SD Myers and those companies. There are some values that stick out. For basically that dielectric strength, we want it to be at least 30 kV minimum. Water content, maximum of 35 parts per million. Now, I want you to understand that a lot of people truly don't look at the water content properly, because water content is a function of temperature. We need to also take the temperature of the oil when we take the sample, so we can actually look at this water content. If the oil is warm, it can hold a lot of water. It'll suck it in, and we can see that there. If the oil is cold, it can't hold the water or the moisture. So the moisture will either be in the paper or in the bottom of the tank. So if I take a cold sample, I may come back with an oil sample where it says the water content is 15 or 20 parts per million, or 15 or 20 parts per million, which is a good number. But if I don't take into account the temperature I'm dealing with, that could still be a bad number. There's just not room in the oil for any more water. Acidity, 0.2 as a maximum. Interfacial tension, minimum of 30 dynes per centimeter. Specific gravity, we want a specific gravity. Those are values that we're looking at and we're going to monitor. There is a company called SD Myers that has done a lot of research in oil, and this is what they come up with, their Myers index number. So they look at acid and they look at interfacial tension, and basically they take the interfacial tension and divide it by the acid number and come up with a number. If that number is 300 to 1500, they say that's good oil. And you go on down to the point where I say, you know what, you need to run, or extremely bad. So you can get a good example at a very quick analysis tool on your own as to whether this oil that you have is serviceable, marginable, bad. You can keep track of how it's deteriorating and take some corrective action. Then there is another set of tests that you should also do. It's called dissolved gas analysis. And these are sample tests. There's a test taken out with a syringe on your transformer. And it's not looking at the quality of the oil. It's actually looking at how your transformer has been operated. And I'm not a chemistry person. That was the class that I had when I was a freshman at Purdue. Didn't like it, didn't do well, did very well in my electrical classes, but not chemistry. Methane, ethane, ethylene, acetylene, hydrogen, carbon monoxide, carbon dioxide. I can look at those gases and the arrangement of those gases and get an idea of what may be happening inside that transformer. For instance, corona. If I see a lot of hydrogen in there, that would be an indication of possible corona, a low energy fault inside that. Sparking and arcing, methane and ethane without any acetylene. That would be a case where I might have an intermittent high voltage flashover, but there's not a lot of current involved with that. I could have overheating where I've just overloaded it, or maybe I've got a hot spot. Hydrogen, methane, ethane, and ethylene could all be indicators of that. Arcing, high current, high temperature internal faults, acetylene would be an indication of that. Now, again, these items, corona, sparking, arcing, probably not a lot you can do about that. You may have to get inside the transformer, you may have to get the transformer repaired, but at least you've got an indication of what's going on. Overheating, if it's not just local overheating, you might be able to correct that with your operational procedures. There are lots of tools. There are DGA analysis tools where they can give you upper and lower limits for each one of those values, and again, what's going on. If you'll notice, though, for a lot of those, there's a big variance between what's normal and what's abnormal. So look at those charts with that, and that gives you a good indication. But there are now some really elaborate tools that can help us on that DGA analysis. Here's what the IEEE says. Here are the standards that we can go through, and I'm not going to spend detail here. You've got this slide. You can print it out, those sorts of things. I've sent a paper out as well. You can look at these. But here's one tool that's used to determine, according to dissolved gas analysis, whether the transformer is operating satisfactorily or whether we need to do investigation, those sorts of things. Then there is another tool called the Rogers ratio. When I take the different components of the different gases and I do simple divisions on those components, I can get meanings that where, oh, this is a normal situation if all my numbers come out like this first line. This tells me that I've got possible corona going on in there. Here I've got some heat, 150 degrees to 200 degrees Celsius. Here's an arc with power. So I would see high concentrations of acetylene in there. Learning how to analyze that. And the lab that you send your oil analysis to does not always do the Rogers ratio. And recently, in my life, it's been around for a while, but in my life, we've been using a tool called Duvall's triangle. The Duvall's triangle goes into much more depth, and you can take the relationship of specific gases, add those three gases together and do percentage ratios and plot them on this diagram, and where they cross tells you what area to be concerned in. That would be a D1, which means low energy discharge. There's some sparking going in there. There are tools on the internet that you can do, look at, and you can put them on your laptop that you can actually even do that analysis when you get the report back. So when I look at all the tools together, the review, if I look at just the individual gas concentrations, basically our IEEE standards and all their other standards, 42% of the time I get a good solution from looking at that, but 58% I'm wrong. If I use the Rogers ratio, 62% of the time I'm right, 33% of the time we really don't know, but 5% I'm wrong. If I use a Duvall's triangle, 96% of the time it'll be correct. So here's what I look at it. So if I can do the individual gas concentrations and the Rogers ratio and the Duvall triangle, if all three of those three things say the same, all those test procedures stay the same, then I have a reason to be concerned about that transformer. So I would encourage you to get involved with those various types of analysis tools. The electrical tests on a transformer, basically the turns ratio, the insulation resistance, make sure that the paper and the oil stuff is good. Winding resistance, make sure that we haven't had the reforming of coil and coil assemblies. A power factor insulation test, which is the first test that we can do that actually will look at the paper insulation as well as the oil itself. And then a sweep frequency response test that will tell me if things have changed in any portion of the transformer during a fault. It will tell you if there's been some buckling of the transformer winding, even if all the other tests come back correct. Okay, with just a few minutes we have left, I want to talk a little bit about circuit breakers. and a little bit about cables. We'll keep it very brief. Circuit breakers, above everything else, operate the circuit breaker at least once a year. The biggest problem with circuit breakers is they don't get operated, and when they need to operate, they don't operate in the same manner that we expected them to. Usually you have a drawing out of a large arc between contacts, okay? The higher the voltage, the higher the arc, which requires media other than air. So circuit breaker tests, I always want to make sure the contacts are good, and to do that, I have to do contact resistance. I want to make sure the insulating medium is good. It could be air, which I can't test the air, but if it's an oil circuit breaker, I can certainly test the oil. If it's a vacuum circuit breaker, I can do some tests on the vacuum. If it's an SF6 circuit breaker, I can do some tests on that SF6 gas. Electrical test, again, always do insulation resistance. Power factor testing to also, again, look at the actual insulation of that breaker. And certainly breaker timing is a great indication that things are not moving as quickly or the same manner that they did when they were new. And if possible, when you do that breaker timing test, do it on the first operation of the breaker. You want to know how that breaker would have operated during a fault condition, and checking it the first operation is your best chance of that. Vacuum chamber, vacuum circuit breakers. I can't see the contacts in there. The best thing I can do is contact resistance and do a high voltage vacuum test on that bottle. Cables, you know, that's the neglected part of our electrical system. We used to do a lot of cable tests back in my utility days. Cable tests back then were high pot, use a high voltage test on that cable. And we quit doing that because we found out that when we were hot pottering our cables, the only thing that we were doing is we made sure that we had a crew available to repair the cable that just failed because we failed it with the test. Now, unfortunately for cable testing, it has to be taken out of service, but there are so many new test techniques. One of them is a tan delta, where I can actually, if I closely monitor when I'm actually testing, I can look at what it used to be when it was brand new and compare what the condition is now. And I can ramp up the voltage, and I can actually shut the test set off if there's any indication that that cable could fail during the test. Very, very solid test. So when cables get to a certain age, we need to be testing those cables to see what kind of life is left. And that 10 delta test is one that can really assist us in determining that. All right, I'm at the end of my slides, and let me look at the time. It's 44 minutes and 19 seconds. I'm right on. What kind of questions do we have, guys?
Yeah, you nailed that time right on there, Alan. There have been a couple questions that came in. The first one, why as a utility should I be very concerned about the customer's electrical system and its reliability?
Now, one thing, I mean, I was the utility there for years. And your customers, you can provide so much assistance to your customers to make sure that they truly understand what their system needs. And if you can help them prevent an outage, oh my word, the loyalty that you've got, maybe the next time a tree falls in your line, they won't be quite as ticked if you saved them $30,000 or $40,000 because they didn't have a problem with their own transformer prior to that. So it's about relationship building and working as a team, because it's in your best interest and their best interest as well that they remain profitable and they have a reliable system.
All right, next question. Can you explain in more detail the reliability versus complexity issues with solid-state protective relaying?
Yeah, I'll do my best. I think the old rotary phone versus the new iPhone is a good explanation for that. But I go back to this plant that was close to my childhood home that was built as part of the wartime effort in 1941. And it's an enormous facility. And back in 1941, all they had were the old Westinghouse and GE electromechanical relays. Like I said, that plant was built in 1941. This is 2020. 80 years later, those relays are still in service. And when we test them, they still function according to their manufacturer's design back in 1940. To me, that's amazing. Now, All they can do is operate on overcurrent protection. That's all they can do. But if that's all this customer needs, that's great. If that customer needed to know what the maximum load was at any given time, if that customer needed to know what kind of harmonics they had on the system, if that customer needed to know what the fault current actually was during that fault, then that relay would no longer meet that service. So you'd have to go to something more complex. So the complexity is going to reduce the longevity of that relay. Again, like I said, these newer microprocessor-based relays, none of them are going to be in service 80 years from now. I promise you that. I won't be around to test them, but they won't be there.
All right, 2 other questions have come in. The first one, are there tools available to assist in maintenance scheduling?
Yeah, let me see if I can get out of this. I kind of had some stuff here that I thought I could help with. We are a part of a group called NETA, the International Electrical Testing Association. They work with ANSI to provide documents that will tell you about how to do maintenance cycles and those sorts of things. And I've taken some copies, probably illegally, out of the back of one of their manuals. But basically, you first of all look at what's the equipment condition that you've got, and then what are your reliability requirements. So they use this little matrix and say, you know what, if my equipment is of average condition and I need high reliability, then this is the number I've got that I got to deal with. If it's in poor condition, but it can be low reliability, then this is the number I can deal with. So these are multipliers. This little simple matrix is a multiplication system. And then you just simply go to the other parts. And again, this is an ANSI NETA standard. And I can actually go to some other parts where it says, you know, let's look at, I've got a liquid filled transformer, okay? It says I need to be visually inspected at least once a month. Somebody will look at that every once in a month, okay? Visually and mechanically inspect it. Just make sure it physically is in good shape, the grounding connections and those sorts of things, every 12 months. And over here in the electrical testing, every couple of years, that transformer, according to this standard, needs to be tested. So if you look at that 24 months, and I go back to the previous slide and say, know what? This needs to be really reliable. I'll multiply that 24 months by 0.5 and say, okay, every year I need to be doing this testing. Or maybe it's in good condition and the reliability is not special, so I could take that 24 months and multiply it by 2.5, which would make it 48 plus 6, 54 months between tests. So there are tools like that that I would really encourage people to look at.
All right, final question. What are the pros and cons of in-house maintenance and contracted maintenance?
Oh, well, that's a good one, because I'm one of those dirty scumbag contractors. Like we're the scum-sucking bottom dwellers in the river there. That's what we are. We're contractors. So the pro for that is like give the work to contractors, because that makes my company profitable. So pros and cons in reality. Pros are, it's like you may not have to buy all the test equipment you need in order to test all the devices you have. Their test equipment's expensive. It's a high cost item. You may not have to have all the expertise, and I mean, you may not have enough work for maybe doing sweep frequency response analysis on transformers to keep a person busy for an entire year. So we can contract that out, and we can use like the 3 weeks we need that person to do that. So that's a real pro for use of contractors. Now, here's a real con for using contractors. And this kind of shoots my own self in the foot sometimes, but you want to make sure that you never lose the expertise in-house. So you need to have the people in-house that truly understand what's going on. They may not have the equipment, they may not do all the testing, but they understand what's going on, because there may come a time when you call me and either I don't get the call, or you call your other contractor and they're busy doing something else. You need to make sure that you really understand your equipment and the maintenance requirements of that equipment and how to understand that equipment on your own. So that's how I see it. Contractors are great. I'm one of those. I love being a contractor. We provide a valued service, but you still want to maintain that in-house expertise to be able to analyze and make sure things are being done properly.
Well, hey, Alan, that was the last of our questions. We want to say thank you so much for presenting to us today. That was some really good information. Hey, if you could you throw up a contact slide for us for those that may want to reach out to you?
Well, sure, I could do that. I think it's right here.
Perfect.
Okay.
There we go.
Yeah.
So, yeah, absolutely. And you know, if you want to reach out to Alan, get a hold of Premier Power Maintenance. There's the contact information. Or as always, you can reach out to myself, Brian, or Ashley, and we can definitely get you in contact with Alan. So again, thank you very much, Alan. We appreciate it. Again, this is our last in the series for this year. We hope you've enjoyed these webinars. We look forward to picking this back up in January. Again, if you have any suggestions, please forward that to us. And with that, we'll end our series, and we wish you all the best this holiday season, and we hope that you enjoy your time with your families and you have a safe Merry Christmas.
Thanks, guys.
Thanks, Alan.
Thanks.
Thank you. Good job.
Thank you.